their joint density function, written as the product of the density functions, of the molecular density function, of the probability mass function, the same thing.
Salud.
And I also mentioned for density functions, if it looks like you can factor your density function into a function of x times a function of y, then you know it is independent. Then it turns out that this, the density function of x, turns out to be, if you can write it as g of x times h of y, then fx of x will be some constant times this function of x, and your density function for y would be 1 over c, that same function, that same constant 1 over that. If you suspect that they are not independent, don't spend too much time trying to factorize it. Just check if you can find a pair of values x and y for which this does not hold. Right, so let's do one more example based on independence. Decide to meet at a certain location if each of them independently arrives at a time uniformly distributed between 12 noon and 1 p.m. Find the probability that the first to arrive has to wait longer than 30 minutes. So I'll give you a couple of minutes to think about this problem. The hint is first to find two random variables. Any guesses what should those two random variables be?
The time that each of them wait?
Exactly. So, well, I mean, not each of them wait, but each of them, I mean, the time when they arrive. Right?
Yeah.
So they're going to arrive, say if X is the time when the woman arrives, and Y is the time when the man arrives. What do you know about the distribution of X? What have you been told?
Uniform distribution.
It's uniformly distributed between 12 noon and 1 p.m. Now, notice your question finally is in terms of minutes. So you want to say it's uniformly distributed. So you can take your time X to be the time after 12 noon that they arrive. So then it's uniformly distributed between
0 and 60.
Exactly. All right, so the same thing for the time of arrival of the man. And then how do you phrase this question? So the first thing we are going to write down is and let's say time in minutes. So since we specified in minutes, now we know that both of them are uniformly distributed over.
Could we take the absolute value of the difference other times?
Yeah, but you can simplify that into writing
2.
what? So okay, so the probability that the one who arrives earlier waits for. I have to wait longer than 10 minutes. Okay, so time between the arrivals is more than 10 minutes, right? The time between arrivals is more than 10 minutes. And yes is absolute value, but that you would write as either y minus
say, yeah, y minus x greater than 10
or
X minus y.
exactly. So write like that. I mean, you can write in the first step that absolute value is greater than 10, but then the next step is anyway going to be.
So we'll end up doing 2 separate things here, right?
Right.
I was thinking of a way to make it like one thing, but you can't.
But how would you? Yeah, how do you calculate?
You're right. It's bad. Yeah.
Because then you would have to know the distribution of the absolute value of the difference of 2 uniform distributions.
Yeah.
So if you want to do that, then we can get to problems where we do that.
No,
too.
it's not actually.
Okay.
Absolutely.
So then this is the method you prefer.
Okay, definitely. Are we going to learn that though, even if we don't want to? Really?
Yeah.
Okay. Great.
Yeah. So you've done the distribution of a function of a random variable, right? Now we're going to do the distribution of a function of 2 random variables. We'll get that eventually.
Sure.
All right. The other thing I want you to notice, the probability of this would be the probability of this, right? Because x and y are both uniformly distributed. So kind of by symmetry, you have that they're the same. So let's just calculate one of these and write it as twice the probability that y is greater than x plus 10. Okay. And so that is by symmetry. All right, so the probability that y is greater than x plus 10. Twice. If I have to calculate the probability of x and y lying in some region, is just the integral over that region of their joint density functions, right? So then your next question should be, well, what's the joint density function of x and y? So clearly to calculate some probability involving x and y, I need to know their joint density function. That is, when x takes this value, does y takes this value also at the same time? So you need to know that joint density function. What is the joint density function for these 2 random variables? And what is it that you can use? The arrival times x and y are independent. Exactly. By independence, we know that if x and y are independent random variables, their joint density function is just the product of the individual density function. So first of all, let's write down what are the individual density functions. This is 1 out of 60, and this is 1 out of 60, and 0 otherwise. So now by independence, since I've told you that the arrival times are independent, I know that their joint density function is simply this. So it is 1 over 60 times 1 over 60, so 1 over 60 squared when x is between 0 to 60 and y is between 0 to 60. Rectangular region and 0 elsewhere. So now this is basically calculus. I'm going to integrate this, the joint density of the two x, y, over the region with a set of all x and y such that y is greater than x plus 10. This is the region over which I integrate. So with calculus, it's always a good idea to draw the region over which you're integrating. So I take this to be my x-axis, y-axis. So between 0 and 60, so initially when I think of what's the region over which the joint density function is non-zero, it's this region, right? Everything in here is where it's non-zero. And it's 0 outside of that. Now, I want to integrate over the region y greater than x plus 10. So let me just draw the line y equal x plus 10. So y equal x plus 10 is going to cross the y-axis at some point. So at what point? When x is 0. Let's graph y equals x plus 10. When x is 0, y is 10, so it starts up here. And then where does this line, when y is 60, what is your value of x? 60, x and 50. So this is the other point where it crosses this region, the boundary of this region. So this is the line y equals x plus 10. So at any value x, this is the point x is plus 10. I'm interested in the region y greater than x plus 10, right? So the region out here above that. So I want to integrate over this region. I mean, that's the region where it's going to be non-zero. Right? So out here 0, out here 0. And so I have to integrate 1 over 60 square over this region. All right. So always try and draw the region where the density function is non-zero, and then the region you're interested in. Right? So the region you're interested. So finally shade the region where the density function is non-zero, and you're interested in that region. All right. So you have to calculate twice the probability that y is greater than x plus 10. Okay. So it's twice this region. 60 square. Okay, so your x goes from 0 to 50, right? So let x go from 0 to 50. So that's going to be identical. And your y, for each x, goes from this line, from a point on this line, so it goes from x plus 10 to 60. And now we just integrate this. So this is twice 1 over 60 squared. So when you integrate this, you get...
What are those integrals? The x one is 0 to 50.
X goes from 0 to 50. From
Why?
0 to 50, because this is the region I'm interested in. Right? This is the region where y is greater than x plus 10 and the density function is non-zero. So up to here. If I integrate from here to here, my my function y greater than x plus 10 is out here, but the density function is 0. So I don't need to integrate that over that region.
What's the integral for y x plus 10 to 60?
So y only goes from x plus 10 to 60. So x goes from 0 to 50, up to that part, and then y goes from x plus 10 to 60. All right, 0 to 50, I get y here evaluated at 60 minus x minus 10. So it's 50 minus x. So that gives you 50x minus x squared over 2, and between 0 and 50, it's going to give you 2, 3, 6, 0, 50 squared minus 50 squared over 2, which gives you 50 squared over 2, and that's just 2. So most of it is just calculus once you set up a problem, right? So here are the important things from the point of view of probability. You first define your random variables the right way, identify their individual distributions. Then of course you've got to set up the question correctly. So the question of interest is you've got to calculate twice the probability y greater than x plus 10. For that, to calculate a probability involving x and y, you need to know the joint density function. So I'm looking for something like this, where you try to calculate the joint density function. How can you calculate that from, okay, so you know the individual marginal density functions. The joint by independence is just a product of these two. Okay? So that's how we're using independence in this problem. We don't have the joint probability density function, but we can find it because we have the individual probability density functions. And by independence, it's just the product of the two. So you have to set this up. So you get most of the credit for getting up to here and knowing that to calculate this probability, you have to integrate, knowing this, that you have to integrate over this region. The rest depends on whether you can do calculus or not. So
that's a 50, that's a 60. Along like a 2. This is like the first one is
here?
First one above it. One above.
Above it?
Go.
So 60. So I evaluate, so when I integrate the second y, evaluated at 60 minus evaluated at x plus 10.
Yeah.
So 60 minus x minus 10. So you end up with 50.
So on the exam, we should get to this point, move on to the next question if we have time, come back and fumble around with the calculus.
Well, this will be worth some points, for sure. Okay, so you will do at some points, but yeah, so if you're not so good at calculus, you better brush up on that.
Is it 1 over 60 because they're going to arrive somewhere between 12 and noon, so at 1 minute they're going to arrive and there's 60 minutes in an hour? Is that like a good way to think of it? Or
Yeah, that's how we derived our density function for uniform distribution.
Okay.
So if it's a uniform distribution, the density function is a constant throughout the interval.
The interval.
Right?
Okay.
And the only constant that would make the integral of that 1 is if you took 1 over the length of that interval.
Okay.
You don't want to think of density function as probability itself. Okay, so it's more the idea that it's just that it's constant. That whole interval 0 to 60. All right. Okay, so that's independence. Right, so next, let me just mention this. So this idea of independence, we've been talking about independence of two random variables. I will not give you problems based on more than two random variables, but I'll just mention that this idea of independence can be extended to more than two random variables. What do I mean by independence when more than two random variables? we can extend the definition of independence. To more for x1, x2, xn, so n here is greater than 2. Discrete random variables, the joint so first of all, the joint, you have to talk about the joint probability mass function. The joint probability mass function is given by, so we denote it by this natural extension. And what does this mean? It just means that this is the probability that x1 takes the value of x1 and x2 takes the value of x2, x3 takes the value, and xn takes the value of xn. That's the definition of the joint probability mass function. We say that these n random variables are independent if the joint probability mass function can be written as the product of their individual probability mass function. So it's just an obvious extension of for all possible n values those n random variables can take. So this might be of use definitely to people in economics, say, if you are interested in the joint distribution of several factors. You might have to construct the joint probability mass function, not just two random variables, but more than two. For continuous random variables, again, the same thing. The joint density function, probability density function of x1 to xn is an n-dimensional function, is a function f such that this function is non-negative for all possible values at t. It's a function on the space of Rn, and it has to be non-negative. What else? We know that if I integrate out, or let me just say, let's integrate over Rn. I think I integrate this function. function for Rn, that should integrate up to 1. And the probability that x1, x2, xn line from set A is simply the integral over the region A of this density function. We're just extending this idea from two variables to n, where A is some region A, some subset of R. Same idea extends to that. Then I can also talk about the joint cumulative distribution function, CDF, distribution function, and random variables. That is just the probability that x1 is less than little x1 and x2 is less than little x2, etc. And xn is less than little x. Alright, and yeah, okay. So, by definition of probability, n-dimensional thing, this is what? This is just the integral over the region A. So this is integral over the region A, negative infinity to x1, negative infinity to x2. And
CDF, continuous distribution function. CDF.
And so again, the fundamental theorem of calculus in n-dimensional calculus is just like if I take the nth derivative,
those are all negative infinity to the.
I'm sorry?
Those are all integrals from negative infinity to the x, right?
Yeah, to x1. So you integrate your x1, your first variable, or maybe I should have used a different variable here, but this one. Yeah. So the first, the first coordinate is integrated from negative infinity to x1, the second coordinate from negative infinity to x2. Alright, so that's just n-dimensional calculus. But if you're in a situation where you're interested in the joint density or joint probability mass function, the joint distribution of more than two random variables, you need to know this. Alright, so I said we talk about the distribution of functions of two random variables. So the simplest function that we will talk about, we will do that separately from general functions, is what's the distribution of the sum of two independent random variables? And I think some of you have already guessed what the formula would look like. Sums of independent random variables. in some situations you have random variables. If they are of a certain distribution, and you add these two random variables, you get a random variable of the same distribution. But that doesn't happen for every distribution. There are a few distributions which you call them self-reproducing, and that means if you add two random variables, independent random variables of the same distribution, you get the same distribution. We'll do some examples of that. First of all, let's look at a general method that we can use to get the distribution of the sum of two independent random variables. Let x and y be independent random variables. We want to compute the distribution, so both the CDF as well as the PDF, probability mass function, of this new random variable, which is the sum of the random variables. And remember, in this section, we're focusing on both these random variables are independent, so that's very important. So again, this splits into two cases, the discrete case. So say x and y have probability mass functions, x and y. So if I want to find the probability mass function of z, so the probability mass function of, forget about z, let me just write x plus y. This is just the probability that x plus y takes the value c. So this is just looking at the situation of the joint probability. I add up the joint probability mass functions where I sum over all x and y such that x plus y is equal to c. By independence, what do I know about this joint probability mass function? I can write it as the product of these probability mass functions. So I'm summing over all x and y such that x plus y equals c. X of x dy of y. And actually I can reduce that formula slightly by saying that x and y, they can vary, but there's a constraint, right? That the sum has to equal z. So that means, so there's freedom of movement of only one variable in a sense. I can let x range over all possible values and restrict y to z minus x, right? So this just reduces to, I sum over all possible x's and look at or if you want, you could have written this as I sum over all possible y's and now restrict my x to z minus 1. So you can use, to find this, you can either use this formula or this formula. So for this function, which is the sum of these two independent random variables, you have a formula. So you could have derived it, or now you can just use this formula. All right. Let's derive a similar formula in the continuous case. With summation, it's always easy, but for the continuous case, you have to work a little harder. Continuous case. Let x and y have probability density functions fx and y respectively, and I told you that they're independent.
Okay, why is this,
Yeah, do it again.
okay. I just understand. So this one is z minus x and this one is z minus y because okay.
Because of this constraint.
Okay, so what do you say? Different?
So I can sum over all y's and make sure x is z minus y.
Okay.
Those make sense, right? I mean, I know even if I hadn't derived it, you guys could have come up with this. But
Yeah, I
for the
could have come up
continuous
with that.
case, okay, for the continuous case, there's a little bit of work. And for the case where we looked at the distribution of a function of a random variable, you can't find the density function directly. So we're not going to find the density function of x plus y directly. What do you think should be our first step? What can be related to probability in the case of continuous? The density function is not probability, right? It's the distribution function. So that's where we will start to come up with the formula. Let's start with the distribution function. So I want a distribution function. So we want to find one distribution function for x plus y, this new random variable. So we will first find the distribution function of x plus y. And then we will differentiate it and come up with the density function for x plus y. So let's say that at some point, so the distribution function at some point z is nothing but, by definition, is the probability that this random variable is less than or equal to this point. Now, by definition of a probability involving two random variables and they're continuous, it's just the integral over the region x plus y less than or equal to 2 of the joint density function. So you start with this, by definition, this probability. So this is not a random variable, this means z. Actually, maybe I won't use z. So let me say, at the point A, so x plus y is less than or equal to this number, I'm integrating over the region where x plus y is less than or equal to that number. All right. Again, these two random variables are independent, so I know I can write this as the product of their individual density functions. And this dx dy. So I can let, if I write it as dx dy, then I can let y range from negative infinity to plus infinity, but now x is constrained to be less than or equal to a minus y. So so y goes from this, so x goes from negative infinity to a minus y. So I'm letting y range over all possible values, x remain less than or equal to a minus y. This is by independence. We get. Let's integrate with respect to x. So integrating with respect to x, you have fy of y, and we integrate this with respect to x. So what do we get here? Fy of y. When I integrate this, what is this? This is just the distribution function of this at this point. Because a distribution function is just the integral from negative infinity to whatever point that is. It's a distribution function at that point. Or in other words, this is just the probability that x is less than or equal to a minus y. All right, so this is a formula for your distribution function, but we want the density function. That we found the distribution function x plus y of a equals integral negative infinity to plus infinity y Alright, so now to find the density function of this, I differentiate this with respect to a. Basically, I just take the derivative with respect to a of that function. So differentiating, we get the following. So differentiate with respect to a to get the density function at the point a. So when I differentiate this with respect to a, I get the density function of this random variable at the point a. On the right-hand side, I take the derivative with respect to a of this function. Okay, first of all, I need you guys to recognize that this is a function of a, here you have a function of a too. Okay? There's no y because you're integrating out y, right? So it's just a function of a.
What was the function to the x?
We're differentiating with respect to a. Okay? So it's f of this random variable at the point a. So it's a function of a. Okay? So we're differentiating with respect to a. Alright, so I differentiate throughout with respect to a, and what do I get? So this doesn't depend on a, so I can take the derivative inside and I differentiate this. When I differentiate this, what do I get? I get the density function of x at a minus y. So this is, and when this is the only thing that depends on a, so the derivative of that is the density function of x at the point a minus y. So this is your formula for your density function of your random variable. Okay, so here's your formula for the probability mass function, the density function. So your density function for the sum of two random variables is this convolution. Now, the same way that you could either write it like this, sum over x or sum over y, you can do the same with the integral. So it could be written as fx of x, fy of a minus x. Alright, so you have your formulas that you can use. If I give you a problem where I tell you you have two independent random variables, you know their individual density functions. If they're independent, then if I ask you to find the density function of the sum, you use this formula. If it's continuous, I ask you to find the probability mass function of the sum, you would use this. Alright, so make a list of these formulas. We're going to use them now when we calculate these other distribution of sums of independent random variables. Okay. So I'd like you guys to go through this. So you have your formulas. I'm just applying them. So using these formulas, find following. X is a Poisson random variable with parameter y, and y is a Poisson with parameter lambda, Poisson random variable with parameter mu, and x and y are independent. Show that this new random variable x plus y is distributed as Poisson random plus mu. So basically it means when you use your formula to find the probability mass function of x plus y, you should get that to be of the form of the Poisson distribution. And so this is one of the few examples of random variables where you have two random variables that are Poisson. If they're independent, you sum them, the sum is also Poisson, their parameters just add. Alright, so go ahead, use your formulas, and try and show that it's, I mean, you already know what the answer should be, right? In this case. So first of all, you need to check what are the possible values x plus y takes. So if x takes all non-negative integers and y also takes non-negative integers, if you take their sum, the possible values are non-negative integers. Values of C and non-negative integers. And for k greater than or equal to 0, we can ask what is Pz of k, or that is what is P of x plus y. What does our formula say? It's sum over all i's. We talk about what the possible values of i's can be. Px of I, Py, this is k minus f. Alright, so now we need to figure out what are the possible values. So you're summing over all values of, okay, for right now we can say I goes from 0 to infinity. You can even say I going from negative infinity to infinity, but you know when I takes negative values, this thing is 0. Alright, if I takes any value greater than k, what happens to this? You have Py of k minus I becomes negative, and we know that this would be 0. So when you're writing it as Py of k minus I, you can say up to infinity, because it's automatically, I mean, that's already 0. But then when you're actually going to plug in what these values are, you should make sure that you sum to the right. Yeah. So up to k, exactly. Alright, let's first write down, just to remind you guys, so Pxi, x is distributed as Poisson with rate lambda, so Pxi is e to the negative lambda, lambda to the I over I factorial, as long as I is equal to 0, an integer. I. And this is e to the negative mu, mu to the j factorial, 1, 2, and 0 outside of that region. So let's see of k. Clearly now, we need both of these entries to be non-negative, so I has to be greater than or equal to 0, k minus I has to be greater than or equal to 0, so I has to be less than. So we only sum from 0 to k, and pxi we can write as e to the negative lambda, lambda to the I factorial, e to the negative mu, mu to the, what was that, k minus I, k minus I. Alright, so some terms that don't depend on I, let's pull them out. So you have e to the negative lambda plus mu, right, and I going from 0 to k. Let's club some terms together. I factorial, k minus I factorial, lambda to the I, mu to the k minus I. I've collected all my terms. That term. Alright, if you don't remember the binomial theorem, this is what the binomial theorem says. Go from 0 to n and choose L, a to the L, b to the n minus L. Okay. So that's your binomial theorem, which is we mentioned first week of class. Alright, so this looks kind of similar to the binomial theorem. You're summing over the right region, 0 to k. So here your n is the same as k. Your a is lambda, your b is mu. There is something missing though. If it's n choose L, I should have k factorial here. And so it's k factorial, it doesn't depend on I. So let me multiply by k factorial, and I can divide out, take it outside the summation sign to depend on I. So if I do that, multiply and divide by k factorial, then what's in here looks like this. 0 to k, k choose I, lambda to the I, mu to the k minus I. And this is e to the negative lambda plus mu, k factorial. This, by binomial theorem, is just lambda plus mu to the k. And you see that this is the probability mass function of a Poisson random variable with parameter lambda plus mu. So you can conclude, therefore, x plus y is distributed as Poisson with weight lambda plus mu. So sometimes to recognize that it has some form, you need to manipulate this a little bit. Right, so even though I say that the final isn't cumulative, you need to remember all sorts of things from the beginning. The assurance is not cumulative. Okay. Okay, so that was an example where you took two Poisson distributions, and if they were independent, then their sum was also Poisson. So in such cases, we say, in this case, we say Poisson distribution reproduces itself. sum of two croissants, you get a croissant, and their rates just add. The next example is going to be of one where you look at the sum of these two random variables, and they're both uniformly distributed, but their sum is not uniformly distributed.
Excuse me, but that's lambda I